So good morning, guys. Today we are going to be talking about collisions. And so it should be on page 15 of your notes. So if you look at my little tiny screen over here, hopefully you can see it. Should be 15, should be blank here. So it should be on page 15. And so there are two main, so you want to write collisions at the very top of your paper, you can do that, right? And so there are two main types of collisions. So this is in your notes right here on page 15 again. So there's inelastic and elastic collisions. So that's what you should be writing down right there. And I'm going to explain what those are quite quickly. Remember, you can pause the video at any time if you need to. So inelastic collision is where kinetic energy, and if you didn't know what kinetic energy is, I failed you a little bit. That is the energy of motion. So kinetic, the energy of motion, is lost. It's turned into a different form. Remember, law of conservation of energy. Energy cannot be created nor destroyed. It just changes form. What does that mean? Well, this is what you need to know. Inelastic collisions occur when objects stick together. They're stuck. Okay. So if you look at on your notes, where you look at the pool, those are that's a pool cue and pool balls, and then there's a piece of clay and a bowling ball, right? The one on the right with the bowling ball before and after, that's an example of an inelastic collision. They stick together, they're stuck. So elastic collisions are when kinetic energy is not lost. So billiard balls, pool balls, bumper cars. So that's when it's not lost. So what does that mean? So elastic collisions are when objects bounce off one another. So the one on the left in that picture down at the bottom, this really dark one here, that is an example of an elastic collision. So inelastic, stuck, elastic, does not stick, bounces off. So I would make sure you label that on this. Make sure you label that an inelastic collision is this one here. And then the elastic collisions, each one of these has their own velocity, and we'll talk about later why these equations, waiting for this thing to catch up with me. Come on, mouse, where you at? Why this equation is different than this equation. So just make sure you write that down. Elastic collisions bounce off one another. Inelastic, they stick together. So law of conservation of momentum. Before the collision is going to be equal to after the collision. So remember, P is momentum, so P equals M times V, right? So you don't have to write this down. Maybe you write down before the collision. I already have that on there for you. You don't have to write any of that down, right? Before the collision and after the collision. So before the collision, each object has momentum, and after the collision, each object has momentum. That's all written down for you on the very bottom of page 15. So this is on if you want to write down, so remember that is an example of an elastic collision, because before the collision and after the collision, each is going to have their own velocity because they're not stuck. That's why the equations are different. So that's the mass of object one, velocity initial. So that I right here, that's the velocity of object one, that's the initial one. And then on the other side, it's going to be the final post-collision, right? And so this is the initial velocity for object two. Okay. So the reason this is different for a inelastic collision down here, is because the object's stuck together. There's only one velocity. So on the one on the right, that's why that is different. So I'm sorry I kind of messed this up a little bit, but look on page 17. So flip over to page 17. This is just a support you can use on a test or a quiz or working problems. You can didn't have to draw a detailed picture, but like you have to draw a picture like that. You can just draw boxes, right? So first thing you want to do is determine whether it's elastic or inelastic. Are they stuck together or are they not? We should probably put this up here, right? So if it's an elastic collision, meaning they're not stuck together because they're going to have their own velocities, right? You would use this formula. So in this example, this would be an example of the one on the top here. This is an elastic because they're not stuck together after the collision. Before the collision, here they smash right here, then after. Okay, you can just mass one, velocity initial one, mass two. So not moving. So you know that the momentum to start out with for this car is zero, right? Because the velocity is zero. After, We want to know how fast the car is moving, right? The final velocity of the car. And this is already done for you in your notes. Just kind of stepping you through it, right? Now we know the mass of the car didn't change. Let's assume it didn't knock off a bumper or anything, right? Didn't lose any mass in the accident, okay? So we can have all the variables we need except for velocity right here. So we can solve for velocity. So if it's an inelastic collision, you would use this formula. It should make sense. They're stuck together, right? So this bottom one after the collision here, it comes from this right here because they are stuck after. So this is here. That's why these masses are added together, because we only have one velocity of this object. You guys can all see all this happening, right? Remember, velocity is a vector. So if it's going the opposite direction, super important. You got to make that velocity the other direction negative. So if a car gets knocked backwards, its velocity is going to be negative. Now, in introductory level physics, most collisions are not entirely elastic or inelastic in the real world. So, but this is just an intro of how these work. Most of the time, they're a combination of the two. Almost done. So here's a practice problem, right? This is on page 16. Again, this is on page 16. So the variables are identified for you, but I want to work this on page 16 for me in your notes. So the mass of the object 1 is 3,000. The velocity at 1 of initial is 10 meters per second. And if I want to be more precise on this, I would say east or make it positive. But since it's going to the right, I'm just going to make it a positive number. Right? This just means movement. This doesn't mean movement. Here they're both moving. So the mass is 1,000. The velocity is 0. Right? Velocity of object 2, this is object 2, is 0. The mass isn't changing of the car. This is post-collision after they've hit. Okay. What is the velocity of the car? We don't know. We want to find that out. But if I know this car is going 15 meters per second, okay, so I have all the variables I need. So this is an elastic collision, okay, because they're bouncing off each other. So I can use this equation. So this is where it's just a lot of steps. So we're just plugging everything in here. I know this is 0, right? This is going to be 0 just by looking at it. So look, these two numbers, these two numbers here, I'm just taking number. This is why it's so important to identify your variables. A lot of students make silly mistakes because they're rushing through. They're not showing their work. This is where they make mistakes, multiplying these two numbers, okay? So labeling your variables is very helpful. So if I simplify this, right, add a 0, that's gone. This is multiplied, right? Plus, just add a 0 here, right, on this number. So now my next step is I'm going to get rid of this 15,000, opposite of addition and subtraction, because there's a plus sign there. What I do on one side mathematics, I have to do on the other. You should be writing this down as an exemplar as well. So now I just subtract this from this, right? Because those are gone. That's going to give me 15,000 equals, sorry, the spacing's messed up, 3,000 times VF1, the velocity of 1. This is why it's so important to identify your variables and write it down and be meticulous. Opposite of multiplication is division. What I do on one side mathematics, I do on the other. So the velocity of the truck post-collision after the hit is 5 meters per second. Now, if I want to be really accurate, I'd say 5 meters per second east. But since I didn't give direction to the problem, I don't need it in the answer. So remember, this is an elastic collision because they are bouncing off each other. Okay, guys, so let's work another example problem here. So this is again on page 16 of your notes. Suppose a Honda Civic. Of course, it's not going to work unless I click on this. Suppose a Honda Civic that has a mass of 1,300 kilograms and is traveling 30 meters per second west crashes head on and sticks to a car that has a mass of 1,500 kilograms and was traveling 15 meters per second east. Please determine the new direction and velocity of both cars since they're stuck together. So it may help keep you organized to draw a little picture. So if you want to answer that question, is it elastic or inelastic? Well, it is inelastic because they are stuck together, right? So if you want to draw something like that, you can. We don't know the direction of the velocity yet. We don't know if it's right or left. We're going to figure that out. If I get a positive number for my velocity, it's positive. If I get a negative number, it would be the other direction. But we don't know. We know the mass. We know the velocities of each, right? So let's go ahead and, so we've got that. So we're going to use this equation because now the masses are stuck together. So you should be writing this down here at least. If a picture helps you, right, draw the picture. This is the left side of the equation here. This is the right side of the equation here, since there's only one velocity. So we're going to see if that's pointing right or pointing left. So the mass of object 1, 1,300 kilograms, is not going to change. It's traveling west, so I made it negative because it's west. The final velocity is what we're looking for right here after the crash. So the mass of object 2 is 1,500. So you should be writing this down in your notes on page 16. So the car was traveling right here before they hit 15 meters per second east. So I made that positive. You don't have to write this down, obviously. Just, you don't have to write that down. Most of you guys know this. I beat this in your head enough this year, okay? So now, guys, here's the deal. You don't have to write down your units, okay, on all these if you don't want to. Oops. So I would recommend probably not doing that. I'm sorry that I should have, before I recorded this, I should have seen that error and taken those out just for simplicity. So notice, this number is going to be negative. This number is going to be positive. Okay, so let's just simplify. Multiply those two numbers, I get this. And again, leave these out if you want to. Plus this times this. If these two numbers multiply, we're going to give me this here. Add these two numbers together, right? They're the same units, so I can simply add them. So now I want to solve. I can add these two together here. They're the same units, right? And there's a plus sign there. So I just added those two together. And it gives me this number here. Notice it's negative. So I want to get rid of these two things on this side are being multiplied. And you need to pause this if you can. If you write this stuff down, you can. Remember, you don't have to write in your units if you don't want to. So we divide by 2,800 both sides. So notice my kilograms are going to cancel, leaving me with meters per second. My velocity final is negative 5.8 meters per second. So that actually means that it's going to be traveling in this direction. So that means west. So the final answer is 5.89 meters per second in the westerly direction. Since I gave you direction in the problem, I need direction in the answer. So, yep. So this is an example of an inelastic collision.
Go, hit it.
Oh no, are you serious?
No way.
Are you serious?